Interpersonal consistency can be described in economic terms as trade consistency, or in epistemic terms as the consistency of agents' beliefs. We study the relation between these two types of consistency in the following paper. The model we are using is a simple type model where we start with a countable state space, finite or infinite, and for each agent there is a partition of the state space into the agent's types. The agent's type in the given element of the partition is a probability distribution over this element. Consistency in economic terms says that certain trades are impossible. The trades we are talking about are simple trades, they are bets. A bet is a state contingent bounded zero-sum transfer, let's say, of money. So in each state of the world, money is transferred between the agents where the sum of the transfers is zero. A bet is agreeable if at each state all the agents expect positive gains. And the bet is strongly agreeable if not only the expectations are positive, but they are bounded away from zero by some constant, positive constant delta. Trade consistency holds if there is no agreeable bet. Weak trade consistency holds if there is no strongly agreeable bet, although there might be an agreeable bet. Finite spaces are simple to understand in this connection because agreeable bets and strongly agreeable bets are just the same. Every agreeable bet is strongly agreeable bet, and therefore trade consistency and weak trade consistency are the same thing. Now we change the economic terms into epistemic terms, and we recall what a prior of a player is. An agent's prior is a probability distribution for which the agent's types are posterior probabilities given the agent's partition. So the types are derived from the prior by conditioning on the elements of the agent's partition. The set of all the agent's priors is a convex hull, is the convex hull of her types. So here we depict it for two agents. This is agents 1 set of priors, and this is agents 2 set of priors. And if there is a point in common of these two sets, this is a common point. This is a common prior. So a common prior is a prior for both players. Consider now this probability distribution, which is neither in agents 1 set of priors or 2. But suppose that the distance of this probability distribution from the set of priors of agent 1 is no more than epsilon. Then we can call it an epsilon prior for 1. It's not a prior, but approximates prior by epsilon. It happens that this point is also an epsilon prior for 2. And therefore, this probability distribution, which we denote now by p epsilon, is a common epsilon prior. We now describe the fact that the two sets are arbitrarily close in terms of common epsilon priors. We say that weak belief consistency holds if for each positive epsilon there exists a common epsilon prior. Again, for finite spaces, weak belief consistency means nothing more than the existence of a common prior, because if the sets are arbitrarily close, since they are compact, there must be also a point which is common to both of them, which is of course a common prior. Now we state some equivalences of consistencies, which is the main result of our paper. The first one is rather simpler than the other one. Weak trade consistency happened to be equivalent to weak belief consistency. This is our first theorem. This theorem generalizes a theorem for finite spaces. As we have said before, weak trade consistency and trade consistency are equivalent in finite spaces, and also weak belief consistency amounts to no more than the existence of a common prior. And therefore, for finite spaces, trade consistency is equivalent to the existence of a common prior. This theorem was proved and formulated and proved first by Morris and then proved again by Samet and Feinberg. For infinite spaces, trade consistency is strictly stronger than weak trade consistency, and our purpose is to find a theorem that find an epistemic equivalent notion to trait consistency. We are looking for belief consistency, which will be expressed in terms of beliefs only and will be equivalent to trait consistency. By the diagram, we can say immediately that belief consistency will be stronger than weak belief consistency. And we might have thought that belief consistency is exactly the existence of a common prior. Indeed, the existence of a common prior implies trait consistency. But the other entailment is false, as was shown by Feinberg. Trait consistency does not imply the existence of a common prior, and therefore, when we formulate our theorem for countable spaces finite or infinite, then the existence of a common prior is a stronger condition than belief consistency. So now we describe belief consistency. Consider a common epsilon prior p epsilon and an element of the partition of one of the agents pi. And we look at the number p epsilon pi. Now, if there exists a common prior, then the p epsilons converge to the common prior, and if the common prior, let's call it p, if p of pi is positive, then p epsilon of pi is converged to a positive number. But if there is no common prior, and the p epsilons do not converge to a common prior, and they spread thin over the whole space, they diminish. Now, what belief consistency requires is that p epsilon pi goes to zero not too fast. More precisely, we look at the ratio p epsilon pi to epsilon. And the more precise, the more of a common prior that p epsilon pi becomes, we want it to still have much substance, so that even after dividing by epsilon, it is big, and we require that this goes to infinity when epsilon goes to zero. This is not required for any pi. It's enough that only one pi satisfies it, and therefore many others. And it should be true for some common epsilon priors, p epsilon. This is the notion of belief consistency, which is equivalent to trait consistency. It turns out that this theorem and the concept of belief consistency is very powerful, because in several examples in our paper we can prove a consistency, that is trait consistency, by showing that belief consistency holds, while we do not know how to prove it directly using trait consistency. So here is an example of a simple state space or type space. It has the elements, the states of the space are just the natural numbers. The partition of agent 1 is given by blue rectangles, and above each of the rectangles we write the type. So for example, p2 and p3 are the probabilities of 2 and 3 in this element of the partition of agent 1. Of course, p2 plus p3 is 1. The partition of the second agent is given by red ovals, and below them the types of in these ovals. This partition structure is well known, and it was used by Rubinstein in his famous email game. Now we assume that all the p's here are positive, and now we define a sequence p1, p2, etc. as follows. p1 is chosen arbitrarily, and it's a positive number. p2 is defined in such a way that the ratio between p2 and p1 is the ratio between p2 and p1, the red ones. p3 is defined such that the ratio between p3 and p2 is the ratio between the blue p3 and p2, and so on and so forth. So we have a sequence Pn. This sequence is called a common improper prior. It induces the types by conditioning, and it's common to both players, to both agents, but it's not necessarily a probability distribution, and this is why it is called improper. Now we look at the various degrees of consistency: the existence of a common prior, consistency, trait consistency or belief consistency without necessarily having a common prior, and finally the weakest of all, weak consistency. And we show how these conditions are, these degrees of consistency are equivalent to properties of the common improper prior P. Common prior exists if and only if the series of the Pn converges. This is almost trivial because if it converges, we can simply divide by the sum and get a common prior. The next one is less obvious. Consistency holds if and only if lim_inf of Pn equals 0. Note that this condition is implied by the previous one because when the series converges, then each Pn goes to 0, then the sequence Pn goes to 0, and in particular, the lim_inf goes to 0. The next one says that certain ratio, the lim_inf of a certain ratio is 0. The ratio is between Pn and the sum of the Pi's that precede Pn. This again is implied by the previous one because when the lim_inf of Pn goes to 0, then Pn divided by the sum is greater than Pn divided by P1, and therefore it goes to 0. Here are examples. If Pn is 1 over n to the k, let's say that k equals 2, then the sum converges and therefore there exists a common prior. If the Pn is 1 over n, then the series does not converge. This is the harmonic series, but 1 over n goes to 0 and therefore it is consistent. If we take Pn to be n to the k for k greater than 0, let's say that k is greater or equal. If k is 0, then it's simply a uniform distribution, 1 for each n. If k is 1, then it's simply n. In this case, Pn does not converge to 0, yet the sum of the Pi's are of the sum of the Pi's that precede nk are of the order of magnitude of n to k plus 1, and therefore this lim_inf is indeed 0, and weak consistency holds. No weak consistency holds if and only if the limit here is the lim_inf is greater than 0. It is easy, therefore, to construct such a no weak consistency P by choosing Pn to be 2 to the n. In this case, this lim_inf is just half, and there is no weak consistency. Note that in the first three cases, Pn over Pn plus 1 is almost 1, and therefore in each element, in each two-state element of the partitions, the probabilities are almost half. In the last case, where Pn equals 2 to the n, the ratio is 2, and the probabilities are 1/3 and 2/3.